By now, you should be used to seeing symmetrical two-dimensional figures, such as the square and the triangle. But what happens to our ideas of symmetry in 3 dimensions? Well, there's nothing unfamiliar about 3-dimensional symmetry. We see it all around us, every day in the real world. Even here in my kitchen, I'm surrounded by symmetrical things. This 6-sided jar is symmetrical, and so is this 8-sided plate. Its regular sides give it its symmetry. Now, before I go any further, I'd better clear up exactly what I mean when I say symmetry. If I hold the plate like this, that defines a fixed space that it occupies. And a symmetry of the plate is a transformation which preserves distances and leaves the plate occupying exactly the same space. For example, a rotation like this, or a reflection in this line. But how many symmetries does the plate have? Well, although this is 3-dimensional, its symmetries are equivalent to those of an octagon, which is 2-dimensional. And the jar here is equivalent to a hexagon. However, there are certain objects here that are symmetrical in a truly 3-dimensional sense. For example, this vase. It has 20 faces, each of them an equilateral triangle. And this calendar has 12 faces, with a month on each pentagonal face. Now, this lamp has 8 faces, and again, each one's an equilateral triangle. This photo frame is a cube with 6 square faces. Incidentally, all of them are pictures of symmetrical buildings. And finally, this clock has 4 faces, and it's symmetrical too, if you ignore the hands. All 5 of these objects have 3-dimensional symmetries, but they're not the only ones. These beautiful objects have 3-dimensional symmetries too. But these 5 are of special interest. They're called the Platonic solids, and they were investigated by the Greeks over 2,000 years ago. They're the tetrahedron, the cube, the octahedron, the 12-faced dodecahedron, and the 20-faced icosahedron. So what are the symmetries of these 5 solids? And how many does each have? For example, if I give the cube a quarter turn like this, then that's a symmetry. And if I reflect it in this plane, then that's a symmetry too. Well, I could count all the symmetries of the cube in this way, all the rotations and all the reflections, but it would be tedious. And it would be even more tedious for solids like the dodecahedron and the icosahedron, wouldn't it? So, how can we make our task easier? What we need is a strategy for counting symmetries of any of these Platonic solids. And that's what we're going to do in the rest of the program. But first, let's review what we know about symmetry in 2 dimensions.
of the Platonic solids have faces that are equilateral triangles. So let's start there. What are the symmetries of an equilateral triangle? Well, they're rotations or reflections which leave the triangle occupying the same space. Let's look at rotations of the triangle first. If I rotate the triangle through 2 pi by 3 radians anti-clockwise, then that's one symmetry. The triangle is left in exactly the same space. I'll label this symmetry A. What other rotations give symmetries? Well, I get another symmetry if I rotate the triangle through 4 pi by 3. I'll label this one B. Are there any more symmetries? Well, there's the special symmetry which doesn't move the triangle at all. Of course, that's the same as rotating through 2 pi, for example. This is the identity symmetry, so I'll label it E. And these are the three distinct rotational symmetries of the triangle. Now, we've described these rotations geometrically, but there's another way of describing them algebraically. We can do that by keeping track of the vertices. So let's see how that works for the rotation A. I've coloured the vertices so that you can see where they move to. And I'll label the locations in the plane 1, 2, and 3. Now, to describe the symmetry A, we're going to list where each vertex starts and where it ends up. So the notation for A is this two-line symbol. The starting locations are in the top line and the final locations in the bottom line. Let's do the rotation again, and this time watch where the vertex at 1 moves to. The vertex from location 1 moves to location 2. So the first column of the symbol is 1, 2. Now, what's happened to the vertex that started at 2? It's moved to location 3. So the second column is 2, 3. And the vertex that started at 3 has moved round to 1. So the final column is 3, 1. And now this notation describes the symmetry A algebraically. What about the other rotations of the triangle? Let's look at B. That's the rotation through 4 pi by 3. What's that in the two-line notation? The top row shows where the vertices start, so that's just 1, 2, 3. And this time each vertex has moved round 2 positions. So the vertex from 1 has gone to 3, the vertex from 2 to 1, and from 3 to 2. And that leaves the identity symmetry E. What's the two-line notation this time? Well, the top row is 1, 2, 3, as usual. But E is the symmetry that doesn't move the triangle at all. So the vertices stay where they are. 1 goes to 1, 2 to 2, and 3 to 3. So these symbols describe the rotational symmetries algebraically. And together these three symmetries are called the direct symmetries of the equilateral triangle. Now, any symmetry leaves the triangle occupying the same space. So if I follow one symmetry by another, that's still a symmetry. So what happens when I combine two of these symmetries? If I start with rotation B through 4 pi by 3, and then follow it by A through 2 pi by 3, the vertices are back where they started. So this combination is just the same as E. We'll use a table, a Cayley table, to list all the combinations. We've just seen that if we start with B and follow it with A, we get E. That's shown by this entry in the table. And the completed table looks like this. all the entries are the rotations E, A and B. And in fact the direct symmetries form a group with E as the identity element. But the triangle does have other symmetries, reflections. Let's look at those now. If I reflect the triangle in this line, then that's a symmetry. I'll label it R. What's the two-line notation for R? Well, the vertex at 1 stays fixed. The vertex at 2 goes to 3, and 3 goes to 2. What other reflections are there? The reflection in this line keeps the vertex at 2 fixed, and the other two vertices swap over. I'll label it S. And there's one more reflection. This one fixes the vertex at 3. I'll label it T. And these are the three reflectional symmetries. Together, they're called the indirect symmetries of the equilateral triangle. And adding these to the direct symmetries gives me all symmetries of the equilateral triangle. There are equal numbers of direct and indirect symmetries, 3 of each. So what happens when I combine these 6 symmetries? Here's the Cayley table as it was before. And now I can enlarge it to include the indirect symmetries R, S and T. And this is how it looks when it's completed. Notice that this table can be divided into 4 distinct blocks. These two contain only the direct symmetries E, A and B. And these two contain only the indirect symmetries R, S and T. And there's something else to notice. Look at the R column in this block. Combining each of the direct symmetries E, A and B with R generates all of the indirect symmetries R, T and S. What does this mean geometrically? Let's take a copy of the triangle for reference. And now do the reflection R. Reflecting the triangle reverses its orientation. So if I now rotate this reflected triangle, I'll get all the indirect symmetries. Of course, if I leave it where it is, that's just R. If I rotate it through 2 pi by 3 using symmetry A, then that's equivalent to one of the reflections of the original triangle. It's T, because the vertex at 3 is fixed. And if I rotate the reflected triangle through 4 pi by 3, using symmetry B, that's equivalent to the reflection S. This gives me a way to find all the indirect symmetries. To get them, all I have to do is to find one indirect symmetry and then follow it with each of the direct symmetries in turn.
Let's now look at symmetry in 3 dimensions of solids like this tetrahedron. Well, each of its faces is an equilateral triangle, so we should be able to use our knowledge of the symmetries of a triangle to help us with the tetrahedron. Here's one of the faces. And here's a better view of the tetrahedron. I'll start by labelling the locations of the vertices. This was the original triangle. And that leaves just one location to be labelled 4. And now I can use the 2-line notation to describe each of the symmetries of the tetrahedron algebraically. The first one's easy, the identity symmetry. Its symbol is this. The vertices stay exactly where they are. And now I can list the rest of the direct symmetries, the rotations. And this is where our knowledge of the symmetries of a triangle begins to pay off. We find that the centre of rotation of this triangular face leads us to an axis of rotation for the tetrahedron. So we get further symmetries by rotating it about this axis. Let's work out the symbol for the rotation through 2 pi by 3. Watch the rotation again to see where the vertices move to. Vertex 4 stays put, and the other 3 vertices move round one. Well, we can write the top line of the symbol straight away. And now I'll build up its columns. 1 goes to 2, 2 goes to 3, 3 goes to 1, and 4 stays put. What about the rotation through 4 pi by 3? It also fixes vertex 4, but this time the other vertices move round 2 positions. So 1 goes to 3, 2 to 1, and 3 to 2. We got those last 2 symmetries by looking at rotations about an axis which fixed vertex 4. But the tetrahedron has 3 other vertices that we could fix. Here, here, and here. And those vertices give us more symmetries. We get 2 more symmetries by looking at the axis through vertex 1. 2 more from the axis through vertex 2, and 2 more from the axis through vertex 3. I've now found 9 rotational symmetries. But are there any others? For a 4-face solid like this, 9 just doesn't feel like the right number of direct symmetries. But for the equilateral triangle, we found that the direct symmetries formed a group. And that's what we'd expect to happen here. So let's try combining some of the direct symmetries that we've found already to see if we get any new ones. Well, it's obvious how 2 rotations about the same axis combine. If I rotate through 2 pi by 3, followed by 2 pi by 3 again, then that's just the same as a rotation through 4 pi by 3. And if I rotate through 2 pi by 3, followed by 4 pi by 3, then that's just the identity. But what about combining successive rotations about different axes? Let's start by fixing the vertex at 1 and rotating through 2 pi by 3. And now I'll fix the vertex at 2 and rotate through 4 pi by 3. Is this one of the symmetries we've found already? Well, the best way to check that out is to use the 2-line notation. So what's the notation for this symmetry? Where have the vertices moved to? The vertex which was at 1 is now at 4, 2 has gone to 3, 3 to 2, and 4 to 1. This symmetry interchanges the vertices at 1 and 4 and the vertices at 2 and 3. The vertices have swapped over in pairs. None of the vertices is fixed, so this can't be one of the symmetries we've listed so far. This must be a new direct symmetry. So what is it geometrically? Because it's a direct symmetry, we'd expect it to be another rotation. But where's the axis? Well, the tetrahedron has an axis of rotation here, between midpoints of opposite edges. If I rotate the tetrahedron through pi about this axis, it swaps the vertices at 1 and 4 and the vertices at 2 and 3 as well. So that's the rotation that the symbol described. But the tetrahedron has 2 more pairs of opposite edges, and that gives 2 more rotational symmetries. So I now have 12 direct symmetries. And that, in fact, is the complete set of direct symmetries of the tetrahedron. Add number 12 is the first clue to our strategy for counting symmetries of solids. The tetrahedron has 4 faces, each an equilateral triangle. And each face has 3 direct symmetries, all rotations. Now, I can choose any of the 4 faces of the tetrahedron as the base. And once I've chosen the base, I can put it down in 3 different ways. 1, 2, 3. So that's 3 direct symmetries for each face times 4 possible faces, giving a total of 12 direct symmetries. So what about the indirect symmetries? Well, here's one of them. Reflection of the tetrahedron in this plane.
Here's the front face of the tetrahedron. This line of reflection of the face becomes part of a plane of reflection of the tetrahedron. Let's take a copy of the tetrahedron for reference. And now do the reflection. The 2 vertices on the plane of reflection stay put, and the other 2 vertices swap over. And now I don't need to do any more work to find the other indirect symmetries, because whatever I do to the original tetrahedron, I can also do to the reflected one, to give me another indirect symmetry. As we've found 12 direct symmetries, there must be 12 indirect symmetries as well. So the tetrahedron has 24 symmetries in all. And now I have the key to our strategy for counting the symmetries of a Platonic solid. The number of symmetries is just twice the number of direct symmetries. But the number of direct symmetries of the solid is equal to the number of direct symmetries of a face times the number of faces. So we can rewrite the formula like this. But twice the number of direct symmetries of a face is just the total number of symmetries, which gives us this formula. That means our strategy for counting symmetries is quite simple. First, count the number of symmetries of any face, both direct and indirect. Then count the number of faces. Finally, multiply those 2 numbers together, the number of symmetries times the number of faces, to get the total number of symmetries of the solid.
So let's just recap how the strategy works for the tetrahedron. Each face is an equilateral triangle and has 6 symmetries. And there are 4 faces. So that's 6 symmetries for each face times 4 faces, making a total of 24 symmetries for the tetrahedron. And now I can find the number of symmetries of any of the solids here.